There we have the second part of Zander's lecture, so excited to hear what it's about.
Thanks. Okay, so yeah, most of this talk will be focused on some applications of the tools we talked about last time. Both some kind of tentative applications in extremal combinatorics, and then also some recent progress on some related problems in multi-party communication complexity. Just to mention, there was also one other application I think is really cool, but it won't fit into this talk, which was like a new combinatorial algorithm for triangle detection. Got some like small savings for like over the trivial algorithm, which requires n cubed time, some quasi-polynomial amount of savings. Like previous works used some regularity lemmas or weak regularity lemmas that got some like logarithmic savings, and then we were able to get some quasi-polynomial savings. And I think that's a really cool work. That was with Amir Aboud, Nick Fisher, Shahar Levet, and Raghu Meka. But yeah, that won't fit into the story today. Mostly today we'll be talking about some extremal combinatorial problems and some connections to communication complexity. So we just start by talking about some sequence of three problems from extremal combinatorics. First, I'll remind you of the problem we talked about last time, 3AP problem. So in this setting, you're given some set A of the integers 1 through n. And the only thing you assume about A is that it's somewhat dense. Okay, and then what we're asking is if you can prove that just by virtue of A being somewhat large, it's forced to contain some non-trivial three-term arithmetic progression. So that's just some set of 3 points, x, x plus d, x plus 2d, all of these points in A. Here, they're just 3 points that are evenly spaced. You're asking if A is forced to contain some configuration like this. So talk about a related problem. Here we have A is a subset of n cross n, so it's some two-dimensional set of integer points. And again, we assume only that A is somewhat dense inside the whole space. And we are asking if this implies the existence of a corner. So a corner is going to be some triple of points again. In this kind of arrangement, they're like form some right angle, and also these two distances are the same. Both they have some distance d. And again, you could write down very explicitly what this pattern has to look like. So it'll be some triple of points xy, x plus dy, and xy plus d. Oh, yeah, sorry. And then before I tell you about what's known about this, let me write down one last problem. So something you'll notice is, well, maybe not until this example, but these are kind of becoming more combinatorial, less about group structure as we go right here. But this is the 6-3 problem. Okay. In this setting, we have some collection of small sets of size 3. So sets of size 3, some sub-collection of that, and then the only thing we assume about A is that it's somewhat large, so it's some delta times n squared. And you're asking whether there's a 6-3. So what is that? It's like a pattern of 3 sets T1, T2, T3 inside A, such that their union is somewhat small. So T1 union T2 union T3 is at most 6. So here's some drawing of this. So we're looking for some 3 sets that are somewhat overlapping so that their union, the total size of all the elements and all the sets is at most 6. Okay.
They could have overlapped on more than one element.
Yeah, so that would be fine. It turns out like you can reduce to a certain case in which these are the things you're really looking for. They look like exactly this. It's true that, I mean, by the definition of the problem, that it would also be fine if you found any arrangement of 3 sets and their union is smaller than 6, or at most 6.
So every 2 is just 1/3, right?
Sorry, I didn't hear the.
No, I said you assume that this hypergraph is linear, that every 2 vertices can belong to the most one, right? This is the okay. Never mind.
Yeah. So that's true. So you can reduce to the case, which is actually justifying. Otherwise, this size bound might look odd to you, but maybe it's more clear when you think about this special case, which it actually captures the whole difficulty of the problem. Is that any 2 triangles, their intersection, or sorry, any 2 of these sets, T1 and T2, say, their intersection size is at most 1. So they don't share a whole edge, they only share a vertex. So if you have a collection with that property, then actually the size is at most 1 squared. So this is showing you why it's like still reasonable to think about it as some like density condition on this collection. Anyway, so here are 3. Sure.
First of all, maybe it's connected to your last comment. Like, if A is greater or equal to n squared, so what's like if delta is equal 1?
So it's known to be true
Mhm.
if delta is equal to 1, and even for like a small delta, I'll write it down. It's like what's known as kind of very mild, but we know that it's true for some delta which does go to 0 as n goes to infinity.
So, but is it obvious why like it not n to the 3rd but n to n squared or something?
I don't know. I guess let's see. I think if there are edges, you can. Yeah.
They belong to 2 edges. So you have 2 edges and 4 vertices in total. So now you need to add only one edge. You are allowed to add 2 more vertices. You need 1 more edge. So it's not so difficult. Because now it needs, I don't know.
If every edge has at most 1 triangle, then it's n squared is the trivial. And if they're edge with 2 triangles, then what the weight said, you can easily get a 6 too. But they're overlapping too.
Anyway, I guess the point is that like with 1/4 of this configuration, and what you say is it's amazing that even little of n squared forces such configuration.
Sure. So and then the challenge for all these problems would be to prove lower bounds and upper bounds on which delta this situation occurs, where you're forced to have this configuration. So let me tell you a bit more about these 3 problems. So these 3 problems are actually like increasing in difficulty, which is, I don't think, obvious to begin with. So if you had like a good value, if you prove this for some specific value of delta, you immediately get both of these for roughly the same value of delta. So let me tell you what's known. So this is okay. X3 problem. So it's known that you can find some pattern like a 6,3 for a delta, which is roughly 2 to the minus log star of n. This is due to Jacob Fox. This is like a small improvement over result by Simonyi, shows roughly the same thing. This is like a exponential improvement over that what Simonyi proved, although in some sense it doesn't get you that far since this is already so slowly growing. But this is the best known for this problem, the 6,3 problem. And here, talk a bit later about why I want to start renaming it, but the 6,3 problem is very closely tied to the best bounds which you can get for the triangle removal lemma. So later on in the talk, I'll start to use these kind of interchangeably to refer to this same problem. Okay, and then we have the corners problem. It's known that delta, which is like 1 over log n, density suffices. This is due to straight up. And then 3AP problem. And we talked about last time that this funny looking quantity, which I'll call quasi-polynomial density suffices. So log n to some constant c. So we proved, Raghu Meka and I proved c is equal to 112. Since then, Bloom and Sisask have improved this constant slightly. And then I'll remind you that the lower bound due to Barond is delta, which is like specifically this particular quasi-polynomial factor with a 1/2.
That's the best lower bound also for delta.
Yeah, that is what I was going to say. Surprisingly, maybe it also happens to be, I mean, there's some small improvements on Barond's construction in like lower order terms, but still only a quasi-polynomial lower bound is known for all 3 of these problems. So it's imaginable that, well, these guys could be substantially improved and you could obtain some quasi-polynomial bounds for these problems as well. Which, okay, if you, if you were here last time, maybe that sounds like good news. We talked about how before, I mean, all 3 of these used to be very far off this lower bound. Just recently, we have actually gotten the right order of magnitude for the 3AP problem with some new techniques. And moreover, these new techniques are really mostly combinatorial and don't rely or aren't so heavily tied to the actual group theory or group structure of this problem. So maybe you can hope that they can be used to attack these more general combinatorial looking problems. And I will say, so in some sense, we have been able to do this, but not quite for these exact problems. I mean, that would be really nice to be able to do that someday. There's some related problems, specifically some problems I can formulate in the context of communication complexity that also, they used to be way off the known lower bound, and recently we got some sort of quasi-polynomial bound for those problems as well. So we start by explaining this first connection to communication complexity. And by the way, for anyone who's not familiar with communication complexity, I'm not assuming any background in it, so I'll go back in a second and define some stuff for you, but let me just say quickly that this corners problem in particular is actually like exactly equivalent to a problem you can state in communication complexity. Specifically, it's equivalent to determining the three-party communication complexity of deciding membership in this particular set. So this set, maybe I should have, okay, so I'm gonna massage things slightly before I move on. We're gonna talk about the corners problem over Zn cross Zn. And also, from now on, when I refer to the 3AP problem, I'm going to think about this version, which is over Zn. This is a very minor assumption, like it's very easy to convert back and forth between this formulation of the problem and this original one, just giving yourself a little bit of extra room. Yeah, with this in mind, this three-party this corners problem over Zn cross Zn is equivalent to determining the three-party communication complexity of this set. So the set of triples x, y, z such that x plus y plus c is equal to 0.
You mentioned that this was, this connection was made in this old paper of Zander first.
Yeah, that is true. So this, I guess was first, maybe Beagle, Gassarge, and Glenn made it.
No.
Oh, I
It's
see.
much older. Zander first and Lipton. They introduced, this is not a standard three-party model. This is a number on the forward model, which they introduced to prove.
That's standard to me, but I
I
see.
know, yeah, but in 1982
I see.
or something.
I see.
But
Okay,
not standard, it was
I see.
very ingenious way of proving low bounds on branching program, which they did, very now low bounds on constant width branching program. And they made a connection to this corners, the Ramsey theoretic problem, corners problem. They used it to prove the law.
Thank you. Yeah, so I guess, yeah, then I do have the wrong reference for that. Thanks. So this connection is due to Chandra first and Lipton, and I'll go over the connection today. It's simple enough to explain pretty much the whole story here. And yeah, so let me tell you, well, maybe I need another map. So let me just give myself some more space. So I want to draw a bunch of problems and kind of relate them all. So here at the top, we've got triangle removal. And then let me put here corners over some arbitrary group G cross, finite group G cross G. And we have some corners over specifically Zn cross Zn. And corners over some other group where there's been some exciting recent progress. That works for various groups, but let me just, for the sake of concreteness, talk about SL2P cross SL2P. Down to 3 ATs. Okay, so yeah, and then so what did we say? This is equivalent to some other problem that's in communication complexity, which is determining the communication complexity this set, let's call it D, which is the triples X, Y, Z, such that in this group, the product X, Y, Z is equal to the identity in the group. Okay. So you could also, yeah, so I'm saying it makes sense to ask for any G, what is the communication complexity of this set here? And yeah, for a long time, this has been a good candidate to resolve some problem in communication complexity, which is specifically to establish some large separation with an explicit function between the power of randomized and deterministic communication complexity. So I will say a bit more about that in a second, but my main point is that if you could prove a strong lower bound on the complexity of this set for any group, that would suffice for this application. So let me draw that third problem down here. This is explicit separation. Randomized and deterministic communication complexity. Okay, and yeah, so let me start telling you which of these problems we have actually been able to claim a quasi-polynomial bound for. So like I said before, it's plausible that all these problems should eventually fall in this quasi-polynomial zone. So the first one we got was this 3AP problem. Then the second one was this problem over here. So we weren't able to resolve any of these questions about corners over any group exactly, but we were able to design some different kind of set which has the right properties to solve this problem. And we got some quasi-polynomial bounds for that problem and got a good separation. And then a follow-up work, let me start writing some citations. So this was, okay, work with, let me write this now. With Shahar Levet and Raghu Meka. Where we were able to get some quasi-polynomial answer to this question. And excitingly, recently there's a work, we get some spellings. Some follow-up work due to Jaber, Levet, and Stooney. Which get a quasi-polynomial bound for this corners problem. And they're going to take this communication complexity point of view. I'm not saying that it's exactly mandatory, but that is what they do in the paper, and they follow our approach in this paper to understanding communication lower bounds for sets that look similar to this one. Okay, so this is the quasi-polynomial zone.
Could I ask something?
Sure, yeah.
It's possible for the corners problem over like a highly non-abelian group that the answer is like the truth is not quasi-polynomial.
That is true. So, and it's kind of yes, it's kind of unfortunate in my opinion. I would like for at least, so one thing that I don't know is that I don't think we have any tight answer for any problem, like any matching lower and upper bounds for any of these problems that have been worked on, as far as I know. I mean, yeah, that would be nice to understand whether that's true or not. But yeah, it could definitely be better. So let me start. Yeah, I'll say specifically they get some delta, which is like 2 to the minus log 1/4 in the exponent. So, I mean, even still, it's not matching the Barron bound if that were to be well, if the Barron bound is unrelated to this heading, but like maybe it happens to be that that's the same lower bound can be obtained. I don't know. Let me say here, like before telling you more about this problem, it doesn't mean much exactly to say this, but like in some sense, translating things, we get some bound which is like it's a 1/3 here. Okay. And I suppose I haven't left myself much. Let me get rid of this guy. Yeah, there's one more workup here, which I'll be a bit vague about what was done here, but it's some kind of removal lemma, and we get quasi-polynomial bounds for it. So for now, I'm just going to call it a slice function removal. This is in some work by myself and Xin Liu. Actually, it's upcoming. Probably we'll post it early next year. Which, yeah, so it gets, well, again, I'm saying this only to try to make the translation of parameters somewhat clear because I haven't told you what this problem is, but there's some sense in which you could hope for quasi-polynomial bounds for triangle removal. In fact, you could hope even to go all the way to Barron type bounds, which would be getting this like 1/2 for the triangle removal problem. And sort of we do get that for this related problem. Again, I don't know if this is optimal even for this setting or if there's any further formal connection, but it's something which is a bit weaker that happens to suffice for this application down here as well. Okay, so
I'm understanding that the Barron bound doesn't transfer to these other bounds.
yes, exactly. So right. So we don't have any tight yeah, the Barron bound is coming in over here at this vertex, and it doesn't you know, it provides a lower bound for these 3 problems that are still outside this quasi-polynomial zone. So yes, unfortunately, I don't know if any of these results are tight. It would be interesting to know. If you're the kind of person to care about the parameter coincidences, maybe you're interested that we get this 1/2 here. But anyway. Oh yeah, and then let me say one other thing. Which is not necessarily related to this map directly, but it's related via the techniques. There's a quasi-polynomial, yeah, I want to advertise this other paper by Yuval Filmes, Ahmed Atami, Kaveh Hosseini, S.T. Kelman. It was like a sparse graph counting lemma. So the graph counting one, sorry, this is due to. Oops. Yeah, and to explain roughly what this is doing and how it's related to the techniques involved in these applications. A lot of these applications, you think about things in just the right way. The main thing that they need from the techniques we talked about last time is that if some graph, it has some, if you have some graph G and it has some mild pseudorandom property, and yeah, so this, so you have some graph G, and you know 2 things about it. It's mildly pseudorandom, a spread. Remember from last time, otherwise it's not so important for this story. With respect to rectangles, and it's quasi-polynomially dense.
You can write bigger, the people who will watch the video.
Sure, thanks. Okay, so it's pseudorandom and it has some quasi-polynomial density. This means that G has like 1 plus or minus epsilon delta cubed n cubed triangles. So with this mild pseudorandom property and knowing that the graph is somewhat dense, we're able to get this kind of, you could also think of this as a pseudorandom property. Certainly a random graph is going to have very close to delta cubed fraction of triples of vertices ending up being a triangle. So we can actually control this count of triangles with spreadness. And what this work is doing is it's proving a similar graph counting lemma that under like the same assumptions, you can control the number of occurrences of any constant size pattern, not just triangles. So like constant, like the number of cliques of size R, you would get like roughly the expected number of them as long as R is like a constant. And yeah, okay, so maybe one other interesting way to think about what they're proving is that that's related to this grid norm is, I guess you could say that if you have a graph and you look at it, it has too few of some pattern, any pattern at all, then, and it's quasi-polynomially dense, then it must have too many complete bicliques. That's kind of what this connection with the grid norm is saying. So anyway, that's
What does the word sparse refer to?
okay, so I take a small issue with this, but they mean quasi-polynomially dense in the sense that previous graph counting lemmas are really only effective for like very, very dense things, like 1 over log n or something.
There was a very influential paper on which defined quasi-random graphs in many ways. It's Graham, Chang, and somebody else, which showed that if you are in the dense regime, let's say constant fraction of the edges of all possible edges, then you just control the simplest pseudo-random thing we know, namely the eigenvalue, second eigenvalue is 0 of n, the 0 of n. Because the main one will be a constant, then you have constant. It's 0 n. Then you have the same conclusion. Every constant size graph, subgraph, appears, 1 plus minus epsilon the number of times. So this is pushing it far, far below the dense regime to this sparse or quasi-polynomial regime under the new pseudo-randomness.
Any more questions about these two boards? Okay.
Maybe you want to say that this eigenvalue being 0 of n is the same as having the grid norm 2 being small. That number of 4 cycles is small. So this natural.
Yeah, that's true. So in this case, the number of 4 cycles being small, you can only measure it additively if you want to use this kind of connection. And then like if you want to study sparser graphs, like ones with quasi-polynomial density, then you really need to start measuring things multiplicatively. And, yeah.
But what does the 4 cycles have to do with the second largest eigenvalue?
It's equivalent. Having a low and second eigenvalue is the same as having
For very dense graphs.
yeah.
The number of 4 cycles.
Constant dense.
The number of 4 cycles is basically the sum of the 4th power of the eigenvalues. I think those are just equal.
Right, okay.
Just a placement.
Okay. So let me tell you a bit about the plan going forward here. I'm going to prove to you these reductions. So I promised you that these problems are actually like reducible to each other. And I'm gonna tell you about communication complexity. And actually, it's gonna be convenient. I mean, this is like ahistorical and you don't need to do it this way at all, but for fun, here is how we're going to do this. So we're gonna prove this equivalence I promised you. And then I'm gonna prove that if you had good bounds for a triangle removal, that would give you good bounds on the communication complexity of this thing. And similarly, I'll show you this reduction here. The way that this is going to go is actually by the contrapositive that if you had a large set with no 3 APs, this would actually give you an efficient communication algorithm, like a low communication algorithm. So yeah, so
Which is also in the original paper.
yes, yeah. So all that is yeah, due to Chandra, First, and Lipton. Actually, I'll tell you, I think it's somewhat interesting that so this proof will also end up being the proof that goes from triangle removal to 3AP. It will be like exactly the same as Semiretti's proof connecting his hypergraph removal to the KAP problem. There'd be like almost no difference mechanically in this proof. And really these two steps combined are roughly just a reinterpretation of that proof exactly how it goes. But we will, for fun, be going through this definition of communication complexity, which I think is a nice way to organize all these problems and how they relate to each other. Let me start with a quick and somewhat sloppy summary of two-party communication complexity, which you should think of as more basic than multi-party communication complexity. We're going to talk about it in a second. So in the setting, I want to think of some set A in a product space. And I have a particular complexity measure of A that I'm interested in, which is the rectangle partition number of A. Which is just going to be like the smallest number R such that this set A can be exactly represented as a partition into some R combinatorial rectangles. And for some reasons we'll see more later, I'm going to like insist that we represent that fact like this. It's like some analytic interpretation, right? So if A is a partition, it can be partitioned into R combinatorial rectangles, then it can be represented like as a disjoint union of them. So I can express this indicator function of A like this. So. Yeah, so this is my first complexity measure. I want to talk about just this rectangle partition number of some set A in a product space. I suppose it's not too hard to imagine some examples of something with low rectangle partition number. You could just write down some rectangles. Maybe here's set A. So maybe more interesting is to try to write down an example of something with certifiably large partition number. Okay. So let's talk about a few examples of that. One would be just this guy here. Just the identity matrix. So A is just this diagonal. Then how can we prove that it has no representation of this form? Well, if it had a representation of this form, then with r smaller than n, say, so this is n by n. Then it would have rank less than, it would not have full rank. And we just know that the identity matrix has full rank. So that proves that the rectangle partition number of the set A is exactly what it seems like it ought to be. The only thing you could do is take a bunch of tiny rectangles which capture all of these points all the way down.
So your R is formally something like truth to the communication.
Sure, so I haven't, we haven't gone there yet, but yes, sure. Right now I just am focusing on this as the complexity measure that I'm talking about. So here is some other example. Sometimes called the half graph. So for the same reason, this guy cannot be partitioned into less than capital N combinatorial rectangles, just because it has full rank as well. Now, something I do want to point out, which is sort of relevant maybe for randomized communication complexity, is that it can be sort of approximated pretty well by a non-trivially small number of rectangles, sort of like by doing this idea. Which is, it's related but not equivalent to the fact that this function has small randomized communication complexity. I'll talk a bit more about in a second. And the same thing is true for this equality function. So both of them have small randomized communication complexity, although for now, I just want you to think about that as meaning something roughly the same as it can be approximated by some small number of rectangles.
And the back here it seems that maybe I'm just missing something obvious, but like a random matrix might require like n squared.
Well, every row is a rectangle, so you can always have.
Yeah. So you could just take all the ones that are in a row.
Of course.
Yeah. So that will give you some limit on this thing. I mean, it's I guess similar to like
Combinatorial rectangles, not real.
Okay, and so now what I want to do is something that complexity theorists maybe are going to think this is a bit perverse, but I'm going to introduce like actual communication complexity as a family of examples of sets A with small rectangle partition number. So that's how I'm going to describe it. Anyway, so let's talk about specifically communication complexity of a set A. So I want to describe it as an example. So think of the following game. So we have a set A. And then we have a party Alice that gets, and maybe I want a different name for my set in this. Okay. So Alice gets some input X, and Bob gets some input Y. and they would like to communicate with each other in order to determine this membership. Is this pair XY a member of this set E? So E is given and known to everyone. When the game starts, they're given some arbitrary choice of X and Y, and they only know their own input, not the other one, and they're trying to communicate to determine membership inside this set E. And the game proceeds in some rounds. They're allowed to communicate like one bit of communication back and forth at a time, and they're like, so A was X and B as Y, and they're going to send each other some bits back and forth, and like each bit that they send will be some function fixed in advance of their input that they have and the communication transcript they've seen so far. Okay, and then the claim I want to make is that whenever you have like some non-trivial communication protocol, so some way of in the worst case over all X and Y determining membership in E, that actually proves that E has rectangle partition number which is most 2 to the C. So sorry, let me say C communication protocol implies that this set has rectangle partition number at most 2 to the C. So this is something that'll be really familiar with complexity theorists, but right now I just want to think of this as a source of examples of non-trivially small, or of sets with non-trivially small rectangle partition number. And so here's some example. In the pure combinatorial sense, it seems kind of trivial, but like it's showing you why this is useful for modeling problems that come from other domains. So suppose X was in F2 to the N and Y was in F2 to the N, and they want to determine membership in this set E, which is defined as a set of pairs X and Y, such that X1 plus up to Xn plus Y1 Yn is equal to 0. So this is just, sorry if you can't see over here, it's just a sum of all the bits of Y, of X and all the bits of Y, and they're asking whether they sum up to 0. So of course, for this simple example, it's not really necessary to have this whole definition in place to see this, but how can, what kind of communication protocol can solve this problem? Well, Alice can just compute this parity of her bits and just send the result to Bob. He doesn't need to know anything else besides just the parity. And then he computes his own parity and then is able to determine membership now that he knows the parity of Alice's bits and Bob's bits. So anyway, what does this end up looking like? We get some matrix. So E is this guy here, and indeed, labeling the rows and columns, right? It's some sort of block matrix that looks like this with a small number of rectangles.
maybe minor for your plan, but you didn't define the complexity, the relation between computing E and computing the complement of.
Yeah, that's true. So it is minor for the plan, and I would like to ignore it, yes.
Anyway, your upper bound in the claim was for both.
Oh, yes, I mean, that's true. So Avi is saying that like something interesting about these communication protocols is like, not only does this give you a partition of E into a small number of rectangles, it gives you a partition of the complement of E, as you see here, into a small number of rectangles, and like the total number is also at most 2 to the C. But yeah, so that will be minor in the story. So let me talk now about multi-party communication. And again, I want to like do this in a sort of a different order than is standard. I want to start by focusing on like the basic combinatorial object, and then we'll talk about like how there's a related computational model that you can think of as some communication game, which naturally leads to low complexity combinatorial objects. So let me fill out this analogy here. So we have some different settings. In the two-party setting, we have some space, which is a product space X cross Y. And we have some kind of collection of basic functions. So in the two-party case, these are just the combinatorial rectangles. So these indicator functions that factor as a product of some test only on X and then only on Y. Rectangles. So this is the object I'd like to generalize. So in the three-party setting, we have some product space X cross Y cross C. And the basic functions will be some indicator functions that can be expressed in this form. So some test involving just X and Y, and some test involving just X and Z, and some third test involving just Y and Z. So these are cylinder intersections. So just to elaborate on the name a bit, we're thinking of these indicator functions that depend on only 2 out of the 3 coordinates as some sort of combinatorial cylinder. And then a cylinder intersection is just some intersection of combinatorial cylinders. You can always write them in this like normal form where you collect together the cylinders that depend on X and Y and X and Z and Y and Z. Express it just like this.
If we draw a cube, people will see the cylinder.
I don't know how to draw.
A cube. Okay.
I have seen the picture that you're thinking of, I think, but I don't know what you can come try to draw some picture if you want.
So this X, Y, this direction. And so I'm looking at this guy. It's a function that depends. So this would be a set. There's one cylinder in the.
Okay, sorry. I thought you wanted
You
me to
could
try
draw
to
this.
draw all 3
No,
at once,
no,
and
no.
then I thought that would be.
Cylinder.
Yes, fine. We can draw just one, maybe, but yeah. So fine. Okay.
I know you could do it.
Need the space. Sorry. Okay. So anyway, and let me just say that once you actually define this, it's somewhat, I mean, this generalization is maybe not obvious that this would be the only choice you'd like to make. Here, the generalization is sort of straightforward. We always have some product space, k coordinates. And again, we have some basic function, which are cylinder intersections. So there'll be just some arbitrary product of combinatorial cylinders. So these things depend on at most k-1 coordinates. Okay. Yeah, so I want to say another thing about these guys. So this is sort of like you could think of as like the global characterization of a cylinder intersection. It's just some intersection of cylinders. It always has some nice representation like this. There is also like a local characterization. Which you could take as the definition if you want. Let me just give it in this three-party case. And it tells you the following constraint. So this is of a cylinder.
I'm going to do it for the standards, but
Wait, let me do this first and then maybe we can do that too. Yeah, sure, why not? Of a cylinder intersection. So in this case, we just have this local constraint that if you have 3 points, x prime y z in S, and x y prime z in S, and x y z prime in S, then this forces this middle point x y z to lie in S. Here's some drawing of this if you like. You could say that like a combinatorial star is just a point with 3 adjacent points one in each one that differs in one of the 3 coordinates. And this condition is telling you that cylinder intersections have no induced empty stars. So they have to actually have this 4th point filled in. And then, okay, Avi is requesting the same thing for the rectangles, which certainly we can do, but I didn't think about it. So I suppose it's just x prime y is in a rectangle and x and y prime is in a rectangle. Tells you that x and y is in a rectangle.
So F, G, and H are indicator functions of a two-dimensional set?
Yeah, just an arbitrary set, but they are indicator functions, yes. Yeah. Yeah, and maybe this equivalence is clear enough. I think, guess I could, should I talk about it? Probably not. Okay. Okay. Okay, so let me remind you. What our goal was to connect this corners problem over Cn cross Cn to the communication complexity of this set D. So specifically the claim, so yes, communication. So the claim that I want to make is that upper and lower bounds for corners correspond to lower and upper bounds for the partition number of this set D. Sorry, because I have one other board over here. So the last thing, definition I need to introduce is just this idea of a multi-party communication protocol. So in terms of the present context, we're going to think about this as a nice way of showing that a particular set has a small partition number into cylinder intersections. That's the role it's going to play currently. It also happens to be approximately equivalent to that, but never mind that. Right? So we can just think about it as like an example of a way to prove that a set has a small partition number. So what is the setup here? So we're generalizing this setup from before where we had Alice and Bob and they're communicating to solve some problems. So here we have K parties and K inputs, X1 through Xk. And okay, part of the setup is that each party to begin with has access to all but one of these inputs. Okay, and then the point of this game is that they're supposed to work together and communicate in order to learn the answer to some decision problems. So they need to communicate in order to learn the answer. Some membership in some set given these inputs, they want to decide if X is a point that belongs to D or not. And of course they, okay, so they're, yeah, like at each round, they're allowed to, you could imagine, walk up to the blackboard and write some number of bits down on the blackboard. And then from then on, it's like public knowledge to everybody what they've communicated. And yeah, like a nice way to think about this is that all of these parties are standing in a circle and they all have like one of the inputs on their own forehead. This is the reason for the name of the communication model, the number on forehead model of multi-party communication. So they all have some input on their forehead. They can look around, they can walk over to a blackboard and write some bits down on the blackboard. And then at the end, they would need to decide membership in D. Okay, and yeah, so what I'm going to show to argue is that if there is such a low communication protocol for a set D, then that implies that D has small partition number. So let me just walk through this. It's a fairly basic argument. Claim is that if this guy has E-bit communication protocol, then this partition number of the set is small. So get some representation of the set D into a partition into some small number of cylinder intersections. And then the proof of this is fairly straightforward once I become slightly more formal about how I'm encoding, like what is a communication protocol. So formally, a communication protocol is, let's encode it like as a tree. So it's going to be some tree which have some input X. It's like a binary tree, which is depth C. So what's happening at all these internal leaves is there's somebody, it's like somebody's turn to talk. So maybe it's Alice's turn to talk and she knows all of the, she knows Y and Z, but not X. She also knows everything that's been stated so far, which is encoded by like this path. Okay, so there's going to be some branch here into two options. So either she's going to go write down a 0 or she's going to write down a 1. And her choice will be determined only by this path and Y and Z. So this would be like some F of XY indicating whether she writes down a 0 or some like the negation of the same function F of XY. Okay, and then so what happens at all of these leaves? So there's 2 to the C leaves, and at the end of the protocol, just part of the definition is that the parties all decide to accept or reject. So some of these paths go down to they say that like yes, X, I think X is in D, or no, we are claiming that X is not in D. Okay. And yeah, so the main point is that I can write down, assuming this protocol is correct, then I can write down, say, this sort of representation, where I sum over all of these leaves. Each one is associated to a specific path. Okay, so maybe I'll indicate this like this. So on input X, we go to some accepting leaf I. And how can I represent this function here? Well, for a given path at each branch, the test is some cylinder, some combinatorial cylinder. So really this test here, whether on input X, you go follow like that.
XYZ.
Yeah, I'm sorry. So yeah, I'm thinking of the most general case, but then sometimes, yeah, so sorry, X is XYZ. So X is the full input. So maybe I'll write that at the very least up here. So sorry. Thank you so much. That's fine. Yeah, so my point here is just that the like the indicator function of following a path to a leaf will be exactly describable as the intersection of C many cylinders. And like it doesn't matter how many cylinders you get, an intersection of any number of cylinders is a cylinder intersection. So this representation finishes the argument here. Any questions about that? So finally, let me start working on these arrows, which I promised you. Maybe let me bring this down and start numbering them. So do this one, and this one, and this one. This one.
While you are erasing that, yes, no, while you are erasing.
Oh,
We have no idea how to prove lower bound for this model if K is bigger than log N. It's a major computational complexity problem. N is the length of each xi or their total length. We have no idea how to prove lower bound and the number of parties is bigger than log N.
Even non-explicitly or just explicitly?
Explicit, no, explicit.
Random.
Random is fine.
so. Okay, so here is the content of this first arrow here. A reduction in one direction showing that if we indeed had some set in our hands, which has no corners and it's fairly large, then this is going to give rise to a way to give an efficient communication protocol for this membership in this set. Maybe be more careful. All right, so we're trying to decide in this restricted computational model, if x plus y plus z is equal to 0. Okay, so how are we going to do that? So the first point is just kind of combinatorial, not talking about algorithms yet. So if A is at least, like its density is at least 1 over m, then this actually immediately implies something apparently a bit better. which is that there exists a coloring of all of Zn cross Zn into, I'll say, roughly m many colors, such that, yeah, maybe with no monochromatic corner. And this is a trick that people, probably a bunch of people will be pretty familiar with, but the idea to form this coloring is just to consider some random translations. So consider a bunch of random translations, a plus y1 for random y, a plus y2. Just as many as we need to guarantee that we can cover all of this space, Cn cross Cn. And then something that's important to note is that this property of having no corners, it is like translation invariant. If I just take the whole set and move it over by some fixed amount, then this condition.
The y's are in Zn for Zn, they are not a y coordinate.
Yeah, yes, right. So maybe I'll name them something else. So just some vectors in this two-dimensional space Cn cross Cn. We just want to take as many random translations in order to cover Zn cross Cn. And then, I mean, we'll get a covering, not a partition. We can just prune some of these sets to get the coloring, right? Because this property we care about, having no corners, it's like hereditary. So that's the first step. So then what do I do with such a coloring in hand? Here. So here's my protocol that will use this coloring C. So I'll call them the XY party, so the party that has access to these two inputs, X and Y, they compute, hold on. They just check what is the color of their tuple XY, and they they spend the number of bits of communication required to broadcast the name of this color. So it's like requiring some log m amount of communication to do this. And similarly, the XC party broadcasts the color of X and then minus X minus Z. And the YZ party broadcasts color of minus Y minus Z Y. And then what do? So they accept if the colors agree. Otherwise reject. So this is the algorithm. It's sort of clearly has low communication complexity, only roughly log m communication complexity. And then what's unclear is why it works. So let me talk about that. So let's check what happens in the various cases. So if you have some triple that indeed sums to 0, then in particular, like forgetting about the colors for a second, like these tuples are all actually the same. So this means that x and y is just the same as x minus z, and that's the same as minus y minus c y. So of course, when they compute the color, they will all still be the same, and then they accept. Okay, and then in the other case, say we have x plus y plus z equals some non-zero element d. And also that all the colors are the same. Then this actually is going to lead to some contradictions. So if you had this happening and yet all the colors are agreeing, then that implies that color of x and y is the same as color of x and y plus d, and same as the color of x plus d, y. Okay, so in this case, we found some monochromatic corner contradicting the assumption. Okay, so we've done one, let's do two, and finally establish this equivalence between the corners problem and the communication complexity of this set over here. So for two, how are we going to do it? Here we're going to say that if this guy is low communication complexity, then we can find a large set A. With no Okay, so let's go through the proof of this. So the proof is going to use this fact that we talked about over here, that if you have low communication complexity protocol, then in particular, D has a small partition number into cylinder intersections. So we can express D as a sum of not too many cylinder intersections. Also, I should say now that this argument, I'm choosing to present it just for the three-party case, but the connection to corners over Zn to the k minus 1 also folds like with these same proofs. Okay, so we have this partition of D into a small number of cylinder intersections. Now, where do we go from there? So let me call these guys SI. So I'm just going to take the largest cylinder intersection in this partition to begin with. So I want to take a cylinder intersection SI, which is at least capturing this density of D. So this is going to be size of the SI that we take. And then we just let A be this like XY marginal, let me call it.
Just reversing the arguments here, right? It's like taking one of the colorings.
Yeah, so I feel like the argument is different, but maybe there's a way to think of it as this.
I mean, what is the partition here to intersection of cylinders?
Yeah, so
each
that will be
color
involved.
Intersection.
So at some point, we're going to use this local, the reason this will work is that we're going to use this local characterization of cylinder intersections. So if you have a proof that doesn't do that, I guess,
Okay.
okay. Okay, so A is just this marginal, and then the question is, why does it work? So like we need to actually prove that A is free of cylinder intersection, or sorry, free of corners. Okay, so we'll prove that by contradiction. So what would happen? So I want to show that A has no corners, but suppose it did. So if A has some xy, x, y plus d, x plus d, y. Then this is going to mean that there are 3 points in S, in SI, which are related. Specifically, we'll get some x, comma, y, comma, minus x minus y. We'll get some x, y plus d, minus x minus y minus d. And so x plus d, y is x minus y minus d. Okay, but now we're in trouble because the fact that SI is a cylinder intersection means that we are forced to contain this last point, which shouldn't be there. We have some x, y, and minus x minus y minus d, which is in SI. Remember, SI is a subset of capital D. So what have we found? We found some point x, y, z in D, but x plus y plus z is non-zero. Okay, so that's this reverse direction. So let me at least sketch part 3. So part 3 is actually going to end up being fairly similar to part 1. Again, we're showing that, say if you had some large KAP free set A in Zn, then this gives you some efficient communication protocol for this decision problem x1 plus x2 k is equal to 0. Now, the reason I switched to k for this case is I actually think it like makes the reduction look less ad hoc for me to tell you the general form of it, but let me just tell you, yeah, so what is this protocol? Oh, again, we start the same way as before. We upgrade this dense set A to a coloring of Zn. with no monochromatic KAPs. So using this coloring, what do we do? Then the ith player computes this quantity alpha I, which is defined as sum over j not equal to I of j minus I xi xj. And they broadcast and they send this to everybody. They send the color of this value to everybody. And then the main point of these values alpha I is that regardless of the situation, these guys are in arithmetic progression. Specifically with common difference d, which is equal to minus x1 plus x2. And so in particular, maybe, they're a trivial arithmetic progression. That's a possibility. And okay, so what do the parties do? So they accept if the colors agree again. I'll skip the proof of correctness this time, but this is the algorithm for some similar argument to before. You'll get a contradiction with the fact that A is supposed to have no non-trivial 3 APs if this algorithm doesn't work. All right. Any question about 1, 2, or 3 here? So before we finally get to 4 and say a couple more things about the actual works I talked about at the very beginning, let me talk a bit about the triangle removal lemma. And in particular, I want to show you some equivalent reformulation of this lemma as a statement which maybe you haven't seen it described in this way, but we can actually reframe it to be about cylinder intersections. So let me tell you about the traditional statement, and then we'll talk about this just cosmetic reimagining of what it's saying. So here's the lemma. So we have some graph G on affiliation, right? We have a graph G on n vertices. And we assume that G has almost delta times n cubed triangles. And then the lemma says that we can find some edge set to remove. So we can remove some number of edges, which is like epsilon times n squared edges. To remove all the triangles. And then specifically, this is some quantitative statement. So we can do this with some epsilon, which is depending on delta, or some epsilon of delta going to 0 as delta goes to 0. Okay, so Currently, there are there's a pretty weak dependence on epsilon. The dependence of epsilon on delta is reasonably weak. That's the best known right now, but I'll tell you like what's plausible. So as far as I know, it's plausible just, because of the Barron bound is giving you some limitation on what's the best thing you could hope for here is that if delta is plausible. Plausible that you could have this statement where if delta was 2 to the minus t, then you'd get some epsilon of delta, which is roughly 2 to the minus square root of t.
Before parameters, I think it's, you start this statement.
Fine.
And you think that
Okay.
it would be trivial to prove.
Wait, why should it be trivial to prove?
Because of the constant fraction of triangles, you may be able to remove it.
Okay, I guess, fine. Maybe if you look at this for a second, the drama is involved in the fact that actually to achieve this, you need to be like removing a lot of triangles per edge, not just like more than like if you picked a random edge, that would not work. I guess that's maybe important.
Basically that's highly non-trivial, forget the parameters.
Well, sure, I wanted to get this because I think it's more concrete just to have something to write down, but.
No, I'm all for the concrete thing, but I'm saying that it's a hard theorem to prove, nobody knows an easy, forget the bounds, anything with this going to zero without parameters. Nobody has even close to an simple proof of this.
Sure, so yeah, the proofs of this, go through like Simonyi's theorem, or at least the weak regularity theorem. So now let me tell you a way of like an equivalent restatement of this lemma. I'm going to restate it so that it's saying something about cylinder intersections. That's like really what it's telling you about. And this really will be like just a cosmetic restatement, except for one minor detail that the triangle removal lemma is like equivalent to a version of itself that only talks about tripartite graphs. So that's the only like, maybe we should do that to begin with, but you just have some vertex sets n, and we have our graph. It's just only has edges here. So the reduction between this case and the general case is fairly easy. You could think of like taking a random tripartition multiple times, for example. But given that this thing really is equivalent, so that this is some restatement. So like the triangle removal lemma. So I want to consider a cylinder intersection. So consider a cylinder intersection. Sorry. So we have a cylinder intersection, and the only thing we assume about it is that it's somewhat small. So if the size of the fractional size of S, which is just given by this quantity here, is at most delta. Okay. Then S can be covered by some cylinders. Reasonably, okay, so we said that this is right, so this is a small cylinder intersection. And what are we going to be able to do is cover it by some reasonably small cylinders. So specifically, we have some pointwise inequality that looks like this by some function capital F, which is some f prime of xy, this time plus g prime of xc plus h prime yz. And then we need to say what is reasonably small. We have specifically this expectation f is at most some epsilon, which is some epsilon of delta. Okay. Yeah, so far this is just some restatement, and then I want to say, in fact, it's really easy for me to tell you the statement of the hypergraph removal with this language, given that I've told you about cylinder intersections over like a product space with k coordinates. It's like the exact same statement. So nothing changes. Is that there's some lemma that Simonyi proved called the hypergraph removal lemma, and it can be equivalently stated as the same statement, just for k is larger than 3. Where you have some cylinder intersection and you want to try to, and it's small, and you want to try to efficiently cover it by some cylinders. Okay. Okay, so with that in mind, I'm going to use this statement to show you this connection 4 here.
Can you explain the equivalency again? First of all, you start with the set that is a cylinder intersection, and then you show, see, what's right here.
Yeah, so what is this, what's happening in this equivalence? This cylinder intersection is just playing the role of the indicator function of a triangle. So in this tripartite formulation, I want to look, certainly something we care about in the context of the triangle removal lemma is the set of all triangles. So this you could just call, so take your bipartite graph.
XY is in the graph. That's the.
Sorry?
It was like f of xy is whether xy is in the graph. What is how you.
Yeah, so let me complete this picture here. But I want to start with my tripartite graph. I'm going to name these 3 bipartite graphs F, G, and H. Yeah.
I understand the assumption. And okay, so I understand the. Okay, sorry, continue to explain. But I don't understand, I still don't see the conclusion.
Okay, so what's happening in this conclusion is that all I'm doing is I'm taking all the edges I would have removed from F, G, and H in this statement up here and bundling them all together into some indicator function that just indicates this subset of edges of F, F prime, subset of edges of G, G prime, and same for H.
Okay, thanks.
Okay, so we're going to just use the triangle removal lemma. Show how it implies bounds for the communication complexity of this problem. And yeah, so specifically, this is some sort of generic reduction. So if at any point you could prove some triangular removal lemma with better parameters, you would get a stronger communication complexity lower bound from the same argument. And like I said, we're going to use this formulation down here. So let me say ahead of time, just I think this is a nice thing to focus on. So what am I going to actually use about this set? X, Y, Z, such that X plus Y plus Z is equal to 0. I'm actually only going to use a certain combinatorial fact about this set, which is that if I draw uniformly at random from this set, this distribution is like pairwise independent. So like it's marginal on any just 2 out of the 3 coordinates, you see everything there. And why is that going to be useful? Well, it's going to be useful because of this fact here. If I have something with this property, I draw uniformly at random from some set D, which is pairwise independent, and I evaluate this on a cylinder. Then actually I'm going to get like the right result. So this test function is unable to distinguish the samples from D from samples from the whole space. So that's like a spoiler of exactly how we're going to carry this reduction out. We just want to use this fact that D is pairwise independent, and because of and this will be the connection with the triangular removal lemma. So let me start. So assume for contradiction that we have in our hands a representation of D by some small communication complexity protocol. I'll call it P, just to have more handles on things. Okay, so what I'm going to do is just look at this representation of P as a partition into some small number of cylinder intersections, and just apply this lemma to each one individually. So I'm going to cover all of these cylinder intersections, which are small. So why is that? So just as an important aside, so each SI is the most the size of D. So the fractional size of each SI is at most 1 over n. So it actually is small, each of these guys. And that means that I should be able to cover them by some cylinders, which are reasonably small. So I'm going to approximate this by some cylinders. So we've covered our function by some cylinders. Now I'm going to look at this quantity. So what is the expectation of X, Y, Z drawn from D of this protocol? Well, ostensibly, it's of course 1, like that's what it should be, according to our assumption at least. So on one hand, it should be equal to 1. On the other hand, this inequality is pointwise, and it lets us get some upper bound on it. So we can get some upper bound of 2 to the C times epsilon of 1 over n, where this epsilon is whatever quantity we have available to us in our triangular removal lemma. Okay, so this is telling you that actually you're going to reach a contradiction. If this communication complexity C is too small, then this will be less than 1, giving you a contradiction. Any question about that?
You get a super constant lower bound of C from without parameters, you just get a super constant lower bound on C because you don't know what epsilon is.
So epsilon is, what do you mean?
Yeah, no, if you just know that epsilon of 1 over n goes to 0 with n, you get a super constant lower bound on C.
Ah,
Otherwise, you get better bound.
sure, okay, I see, yes, you get a super constant lower bound on C. That's true. So in particular, like since all these things are related to like the corners problem, then you get some sort of answer to the corners problem, some sort of delta going to 0 as n goes to infinity from this argument, okay? And then 10 minutes. So what I want to tell you about is how the results we've proved since then about some related communication complexity problems follow this sort of same paradigm actually. So let's try to talk like abstractly what was important to carry out this plan. Which relied on the triangle removal lemma. So even more abstract than the triangle removal lemma itself was this fact that what did I want D to do? I wanted D should be evasive for small cylinder intersections. So, for example, in the context of this problem I talked about earlier, trying to separate randomized from deterministic communication complexity with an explicit function, something you could try to do is just like design another D, of your choice, that somehow, I mean, for the application, you would like it to still be easy for randomized communication complexity, which we were able to do, but D just has some property that allows you to prove better bounds for this kind of thing. You can show that it's very evasive where, so what does this argument tell you is that if D is pairwise independent, this is some sort of pseudorandom condition. It's sufficient for this other kind of pseudorandom condition that it's evasive for small cylinder intersections, but with fairly weak parameters. So we're able to get quasi-polynomial bounds for some slightly different sets D. So in before, let me just write down what the construction is. You shouldn't focus on the details too much. Really, we only like needed to engineer it to have some combinatorial features. But I will say that D is this set. We pick some different set D, and again, we're trying to show that it's hard, that has high communication complexity. It's this set X, Y, Z in a second. I should write this. So it's in some constant dimensional vector space over a finite field, still a product space with 3 coordinates. And the set is the set of points such that all of these inner products agree. So X, Y, and X, Z, and Y, Z. Okay, and then the main result that we're able to prove is that like D is evasive for small cylinder intersections. Specifically, if mu of S is at most 2 to the minus T, then show that the measure under the set D is roughly almost to the T to the 1/3 here. And then say one more example here. So this more recent work. They show that for this set D, which is X, Y, D over SL2P. That the same kind of statement that this set D is evasive for small cylinder intersections. So if mu is at most 2 to the minus T, then the measure under the set D of this set is at most 2 to the minus T to the 1/4.
Because of the structure, it gives a bound on corners in this.
So this is the point of view they take, but everything that we've talked about, I mean, we talked about corners over Zn, but this argument I gave was completely generic. So this, by doing this, can work back through these connections here to get some bound for the corners problems. This is the point of view they take in the paper. Let me say a couple of remarks about so what did we use? So here in this argument, the thing about D, the combinatorial fact about D that was used is that it's pairwise independent. For KLM 24, we needed a set D, which is approximately pairwise independent. Even after conditioning on some large subcube, X prime, Y prime, Z prime. So that's the property of this set D that we actually care about for this work. It is just this combinatorial fact, and then given that, the rest of the proof goes through, and then here even though they have this very specific construction, the only thing that they really need about this set D is that D is, well, they use two facts. So D is pairwise independent, and that D is pseudo-random with respect to subcubes. So with respect to these test functions that look at some product test on X prime, Y prime, Z prime.
The second property follows from the fact that it's a large irreducible representation.
Yeah, that's a so-called quasi-random group. That's right. So that's how you get the second property, but they only need these two. So it's not entirely comparable, but roughly the combination of these two facts is weaker than this, making it a stronger result. Makes sense. Yeah, like I said before, this application to corners over any group of your choice would have sufficed for this communication complexity application. But yeah, that was proved afterwards. Okay, so I think I could say one more thing if people wanted to hear, otherwise, what do you think?
Just you're almost out of time, so you can have a couple more minutes.
Okay, yeah, I just wanted to say something about this guy here. So in a related follow-up work, we really kind of this is with Xin Liu from Berkeley. We really distilled what was going on here, I think, and we have some like different version of the proof that gives a kind of lemma which is comparable to this removal lemma. So it's a let me just write that down and then maybe it'd be done. But it's kind of hard to compare to this version, but it's easy to compare to this version. It's some sort of upper bound cover for cylinder intersection. Just very quickly, so I need a definition. I'll just give a definition by example. So a slice function. It's a function that looks like this, let's say. Okay, so it's more general than a cube, but less general than a cylinder intersection. It's just some product of two functions that depend on different variables. Okay, so this is a slice function. So this is our slice function. Lemma. So again, same as the setup here. We suppose that we have S is a small cylinder intersection. So let's talk about here. Okay, then we can give a cover. So S can be covered by some slice functions of reasonably small total size. Here we have this pointwise upper bound. Which is just a bunch of slice functions. And specifically one where this R is at most 2 to the poly T, and this size of F is roughly 2 to the minus square root T. Okay.
So you are replacing edges in the removal lemma by edges and some subset of the vertices of the third group.
Yes.
That makes your cover smaller.
Well, sure. Although, I mean,
You still need to cover, yeah.
so I mean, the original thing is plausible with these parameters as well.
Yeah.
So,
Yeah, I'm just trying to understand why you gain this advantage and then.
I mean, like, I don't know, I guess we gain it for technical reasons or something, but this shows you something interesting that, so from a pseudo-randomness point of view, this is like some, you know, sandwiching approximation. It's telling you one-sided result, which is that how can you be evasive for cylinder intersections? Well, it suffices to be evasive for slice functions. So that's the pseudo-randomness point of view on what we prove here. But something really interesting, like an open problem, I think, is to try to prove this for k larger than 3. So we really can't do that. I kind of view this as like a sort of intermediate problem that should be roughly easier than like KAPs, like getting really good bounds for KAPs for k larger than 3. I think this is something you should try to do first, maybe, but maybe if you're interested in purely combinatorial approaches, that in that case, I'd be confident in this statement. But anyway, yeah, so this is due to myself and Xin Liu. It's some upcoming work that we should post next year. Okay, thanks everyone.
What questions before we head to lunch?
I talked enough, but I still have a question. In this last open problem you mentioned, how is the difficulty of this related to the difficulty of proving a better, bound for 4AP?
That's what I was saying. I think that it should be easier that's my, I mean,
It's easier than the 4AP, but proving this for 4 will be easier.
I think it should be. I mean, I think maybe technically they're incomparable, but especially if you really wanted to use like some combinatorial only approach, like maybe this is, most people are not doing this, right? Like only Semiretti's theorem is really attacking it by a purely combinatorial approach. Maybe you could say that finally they're like these new works are really attacking these problems which look somewhat about group structure really just from a purely combinatorial approach. I think that's fair to say for those. So at least in the context of combinatorial approaches, I think it's definitely easier. And yeah, I mean, I guess another open problem is just to separate for k larger than 3, randomized and deterministic communication with an explicit function. That also is like, I mean, this is like I think a reasonable route to doing that, but it's also an open problem.
Okay. Thank you.
Thanks.